transferred. Yeah. Regarding that, here's a bunch of problems that have been discussed at office hours, more or less. Of course, the people who've been at office hours know about them. So I show you guys some of these problems without giving solutions. I would say interesting problems discussed at office hours, really quick. So one was a recurrence. Somebody asked me, P of n is P of n minus 1 plus P of n by 8 plus square root of n. I don't know if we solved this problem or not. I don't know. I don't remember who asked me that, but somebody did. And there's some people having interesting ideas. Not an answer yet. Another problem being discussed is something I mentioned in class, the majority element. Has to have the count at least n by 2. But in general, a dominant element has to have a count at least n by 10, say. So the difference, this is a little harder problem because majority, if it exists, it's only one, let's say strict. While dominant could be 9 elements that could be dominant. So here's what somebody proposed how to solve this problem. We have to find that in a string. So it's in linear time. As I have a stream of numbers passing by, I have to keep track of a dominant element. But there is a constraint here, use constant additional memory. Additional really doesn't mean anything because the stream is the stream. So additional means apart from the stream. So here's an idea. I think somebody mentioned this at office hours. Keep two arrays. One is with, say, 10 values and 10 counts, their counts, as I see them. So there's V1, V2, up to V10, and count 1, count 2, count 10. And when a new element comes in the string, I'm going to check to see if it's one of the values I have. Those elements only, the only comparison allowed is value Si equal to value Sj. So there's no other type of comparison, it's bigger or smaller. So when a new element comes in, Si, some part of the string, right? I check against if it's one of these values, and if it is, I do what? I increase the count, right? But the person who proposed this to me yesterday, I think, was saying, what happens if an element comes in and is not one of these? So that's all of one operation, right? Checking against those 10 values and increasing the count. It's a constant time operation. There's only 10 of them. What if this element is not in my table? At some point, I need to change the values in the table, right? I mean, I may kick out an element and put a new one, a new value in. If I put a new value in, what will be the count? 1. But then, what if I kicked out the wrong value and that happened to be a dominant element all the way to the end? This is the part that's still foggy, I think people are thinking about it. Now, this problem is a PhD scope. It's not master level scope. It's saying that's been discussed. This was one of the written problems in the past. Another problem that has been discussed intense at office hours was this problem 16.2.5. there's a bunch of values on a line. A1, those are given. A2, A3, A4, A5, A6, A7, so on and so forth, right? So the array A is given. And the task is find minimum count M of intervals, unit intervals. So these are intervals of the kind from T to T plus 1, right? To cover all the array. So I may have an interval here, another one here, and another one here, for example, right? I want to optimize for the count how many intervals I need. Right? So although I have a lot of values, I may need only 2 intervals if those values are good, for example. And I think most people find a solution that's in. That's obvious, right? As in, if I sort those things, there is a greedy solution that passes to those. Start from the beginning, I go plus 1, and then what? Well, I have to go to the number, something. I think my intuition is that after the sorting part, assuming we sort the array, it's only linear.
Yes.
I'm not sure. Just say, I think it's linear. So that makes me think sorting may not be necessary. As in, the problem doesn't ask you to sort the numbers. Of course, if you sort them, you can do it after the linear time. My question is, can it be faster than n log n by somehow not sorting? Or at least in particular cases, like suppose there's a fixed
discrete
range or something like that, you know, or some distribution over the numbers will allow me to do this faster than linear time. That's another problem being discussed. So today we'll start to the recap here. So for a bunch of problems that we're talking about 4 or 5 problems already, we have this idea. So I'm going to start making more specific statements than last week. We want to characterize optimal solution without seeing it, without computing it. So this is a theoretical exercise. Saying if somebody gives me the optimal solution, what properties that has. It doesn't ask you to compute optimal solution. It's saying if somebody shows it to you, what do you think about it? So we said the optimal solution is some sort of decision plus a solution to a subproblem. There may be many, several, plus some combination. It may be that decision and the combination are the same step. Sometimes, once I make a decision, I have to solve the subproblems and combination happens naturally. So I can also think, that's what we did last time. I want to think in terms of the optimal solution right here. I could think of a decision as kind of a breaking point. This is a decision. And I can think of this as a subproblem, say 1, and this as a subproblem, two. I may have multiple decisions. I may have another decision here. And in this case, this is a problem K. And the combination is the way they glue back together. Again, that sometimes it just happens naturally, like in merge sort. They don't happen naturally. In merge sort, once I break into parts, I solve the parts, I have to put it back together. But in quicksort, I don't have to put anything together. Once the sorting part sort, after the partition, it's just sorted. Right? So I want to think about it this way, and the characterization includes a few things. So that's we're going to go call this part one. It's going to say an optimal solution. It's 1A. Optimal solution implies it is optimal for subproblems. So for me to do divide and conquer here, I have to have that if somebody gives me an optimal solution, that's optimal for the chunks. What was this with respect to the activities problem? If this is optimal from the beginning of time to the end of time in terms of activities, if there's a maximum number of activities that can be scheduled, if I chop off the time from, say, so this was 6 a.m. to 10 p.m. at night, right? If I chop off the time into 3 chunks, that optimal solution, number of activities scheduled, was optimal for this chunk, optimal for this chunk, and optimal for this chunk. How many people remember that? Okay? But what were the decision points? If I have to think about like that in the activity selection problem, I have the time from here to here, and those are a bunch of activities, a bunch of activities, a bunch of activities. The condition is that they cannot overlap. Right? The decision that makes sense is between 2 activities, right? To make this kind of characterization, I have to pick a decision that's between activities. If I have an activity here, another one here, and another one here, another one here, right? If I cut the time on top of an activity, right? If I say pick the decision point in here, I can't really make this characterization because subproblem 1 have 1.5 activities. That's invalid. It makes a lot of sense to pick the decision point between the activities, right? Then say from here to here, the optimal solution must be those 2 activities. Again, why is that? If this is not optimal, if somebody can schedule 3 activities instead of 2, I use an exchange argument. If this can be done better, I swap this part, the other 2 stays the same, and then I get a better solution overall. Hands up, who's with me? How about the knapsack? If this is an optimal solution for the knapsack, where does it make sense to chop off the knapsack? Think of the knapsack as the capacity, right? Z. And solution includes a bunch of items with weights and values, right? Again, I have the optimal solution, somebody gives it to me, and I say, okay, you included so much coffee, so much grain, so much sugar, so much. What would make sense to chop? How do I chop off this knapsack now to characterize the optimal solution? So if this part of the knapsack is, say, coffee, and this part of the knapsack is sugar, and this part of the knapsack is flour, and this is grain, and this is tea, right? It makes sense to chop off the knapsack between those items, right? And then how do I say this is a problem? This is the subproblem of having only that capacity and with maybe all items available. How about this part of the knapsack? It's only having that capacity, but only with items that are excluding those 2. Right? Because I don't have more coffee here. So on and so forth. Right? So you gotta do this analysis. This is required. As in, even if you write the perfectly correct solution or proof, if it's a greedy problem, if you don't do this, you're gonna lose points. For any divide and conquer problem, you have to do this analysis first with respect to that problem. If it's activities, you talk about activities. If it's coin change, you talk about coins. If it's knapsack, you talk about items. But the first thing I want to see in your paper, exam, homework is some notion of, here's how I think of an optimal solution if somebody is to give it to me. Okay. So there's another point, that's part 1B here, that if I have the optimal solution for subproblems, I can obtain the optimal solution for the whole problem. You can say that's the combination step. In other words, if I know how to fill this chunk of the knapsack, and this chunk of the knapsack, and this chunk of the knapsack, that somehow those, if somebody tells me how to fill those parts, I can put that back together into how to fill the whole knapsack. In activities, if somebody tells me what's the best way from 6 a.m. to 1 p.m., and what's the best way from 1 p.m. to 7 p.m., and what's the best way to schedule activities from 7 p.m. to 10 p.m., I can put those together and get the optimal solution. And there is a part C in here. We're still at part 1, which is the decision is a question. Decision requires solution to subproblem, question mark. If no, that means grade 4. If yes, that's dynamic programming. I'm going to call it DP here. And that implies some sort of search. Search for decision. It's not always that implies a search, but typically, depending on the solution to subproblems, I need to see where the decision is. I need to say, okay, try different decision boundaries and see which one is the best. In greedy problems, I can make a decision a priori. I don't have to search for it and then just solve the subproblems, right? In activities, we make the decision effectively by saying pick the activity by the following greedy criteria. And that was done, the decision. That was the first activity, right? And then we solved the subproblem after that, the remaining time with the remaining activities. Same thing in the fractional knapsack. We said pick the item by some greedy criteria, that's the decision, and then deal with the rest of the knapsack later on. See how much capacity you have left, what items you have left, right? In dynamic programming, we can't do this. We don't know how to make a decision before we actually solve the subproblems. That means, how can I solve a subproblem if I don't have a decision, right? Think about that. You're going to say, okay, in dynamic programming, if you don't give me a decision boundary, how do I know which one is this subproblem? And that's why we need a search. We're going to say the decision can be here, or can be here, or can be here. Right? Try all 3 of them, see which subproblem you get. Depending on the results, pick the right decision boundary. So, characterization of the optimal solution is some discussion like this. And I'm going to print some PDFs of some of the problems we discussed here. I think they're online already. And maybe if you want, even for some homework problems, we can give you solutions in an electronic form. But before the midterm, I can print some selected problem solutions, and you guys can pick them up in the papers. Just to see what's a more formal way to solve those problems, including greedy proofs or something like this. So that's part 1. Now, I'm going to talk only about dynamic programming. So in greedy, we did it last week. In greedy, if I'm in greedy world, I make a decision. Typically, it's an efficient algorithm. Typically, the subproblem is a very simple part. Once I make a decision, I have the subproblems already. Go ahead and solve them. But I need a proof that that greedy thing works, meaning at the end of the day, I'm going to end up with a maximum number of activities. Now, let me add something here. This is our midterm collection so far. Activity selection problem. Maximize not the number of activities, but the total time. So I have the same problem, bunch of activities, but instead of maximizing how many activities I do, which is what we did last week, I want to maximize the total scheduled time. Meaning, if I look at the time, there will be some time with activities in it and some gaps between them, right? I want to maximize the time, minimize the gaps. So that's an interesting problem. Or I think I mentioned another one, activity selection problem, but we have 3 venues. So you got a conference and or Olympic Games, right? And if you have only one TV channel, you back to activity selection problem, how many things you can schedule. You don't want them to overlap, because if you overlap, people don't see the whole thing, right? But if you have 3 channels, your NBC 1, NBC 2, and NBC 3, you can schedule activities on 3 channels, right? And then I still have activities. On one channel, they cannot overlap, but between the channels, doesn't matter, right? So I have 3 venues. Or if you're at a conference, you schedule events, you have 3 events or something like that. Is it still greedy problem, or is it no, dynamic programming problem? That's, all those are for you guys to think about. You have about, what, 2 weeks or so to solve all that? Okay, so now dynamic programming. The first problem we're going to do is coin change. I think you had some version of it in the homework, maybe, that's greedy, but the general coin change problem is I have D denominations. So D is D1, D2, up to DK, I believe. I'm going to put the same index that we have here. Yeah. And I have n cents that I have to break up into some form of D I1, D I2, D IB, or something like this, right? So I want to give change denominations infinite number of coins. So I have a lot of quarters and pennies and dimes and all of that, right? So he's saying, in United States, what are the denominations? 1, 5, 10, and 25. Right? So I get n cents. This is a fixed array. So I give n cents, I give coin. I think you have a question that says with a particular set of denominations, this can be done greedily. Greedily would be, what's the obvious greedy choice in here? Pick the maximum denomination, give that coin, and deal with the rest. So how do we think of the optimal solution? I'm at part 1 right now. So P1. Put the P here, P1. Optimal solution. If n cents can be written like this is n. So I have a bunch of coins here. Maybe that's D1, that's D1 again, right? We have a few D1s. D2 up to DL here. And then maybe I have a DK. If this is the optimal solution. Optimal, we mean we want 1. So the objective is minimum number of coins used. If I break it somewhere, so part 1A, if there is a boundary here, these two have to be optimal. Right? So if I split this, this is all n, this is b and n minus b, say cents, right? So split optimal solution n into b, n minus b, such that this is between the coins, right? With the b, it's sum of coins. In optimal solution. So I'm not picking a random boundary. I'm picking one that's after a bunch of coins in the optimal solution. Again, this analysis, I know I've said this many times, you assume you have the optimal solution in your hand. So I pick any boundary in the optimal solution, I say, then the optimal solution restricted to the B part and the optimal solution restricted to the n minus B part, those have to be optimal for subproblems. In other words, if that was optimal for the whole thing, this giving change to B cents and this giving change to n minus B cents, those have to be optimal. If there is a better way to do this, meaning a smaller number of coins, then I can update the whole solution and get a better one. Exchange argument, right? Instead of how many coins are here, I can use less, then I can replace that back, I get the better solution. Now 1B, if I can solve B optimally, this is the B part, and n minus B optimally, and if B is chosen correctly, then I get an optimal solution. If there is some magic boundary that I don't know yet where it is, such that if you solve this problem optimally and if you solve this problem optimally, putting it back together gives you the optimal solution of the whole problem. The only trick is what? The only unknown part in here is how do we find the decision boundary? Right? Where do we break this problem of n cents? I give you n cents, n equal 300. If you know, if magically somebody tells you break the 300 at 175, then you immediately say, go ahead and solve the subproblem. Solve the 175, solve the remaining, which is 125, and then whatever number of coins you get there, whatever number of coins you get here, you put it back together. Right? Question is, how do you know? What this is saying, effectively, there is such a B. Are you following me here? There is a magic B. How do we know there is a magic B? We don't know where to find it, but this part promises there is such a B. How? We look at the optimal solution, and what the part 1A and 1B say, if 1A, part 1A says, if you see the optimal solution, you can pick a B between the coins that you have. Right? So there is such a B, but you can only put your hands on it if you see the optimal solution. So in here, part 1C, we have to decide which one is it. Can you choose this boundary in advance and then go ahead solve the subproblems, which would make it greedy, or we have to search for this boundary. So what is it in here? We have to search for B. For the decision. Now, we're gonna pick the decision to be after the first coin. We still have to search for it. We don't know which coin is it, But we don't need to search all paths. I mean, we can break it anywhere we want. The first part says no matter if you break it here, here, or here, here, you get subproblems, and if you solve those subproblems, you get back a solution to your original problem. We're going to look for this boundary. So I'm moving on to part 2 here. That is recursive definition of objective. As a requirement, we have to call this C. So you have to use a capital C for this, not a different letter, and you cannot use C for anything else. So in all your solutions from now on, capital C must be the objective recursive definition. Because the TAs will look specifically for this C, and if you call other things C, it will be confusing, right? So you gotta use the letter capital C. This is a big C. So we're gonna write these mathematically with the recurrence. We're gonna say, C, what are my parameters? I'm gonna say the only parameters we have is N. The reason these are not parameters is why. As I move to subproblems, they do not change. The reason it's only N is because these is fixed for subproblems. I have these, but they're global variables. They don't change. When I move to a subproblem, fewer cents, I have the same these as before. So I don't need to use them in there, right? Now, let's assume we have this boundary, B. How do I write? The objective is always the value that you want to minimize or maximize. So in here, C will be in English what? Number of, optimal number of coins. That is C. So this objective is always what you want to maximize. In the discrete knapsack would be the value. In activity selection will be number of activities, right? In the guy with the water bottle that's trying to stop on the highway to fill his bottle, you know, number of stops, right? So this C is what are you trying to minimize or maximize. So what is it? If I'm looking for this decision boundary, B, I already said I'm looking for one after one coin. I could choose any decision boundary. I can look for this one, but I think it's easier to just look for the first one. If I have this decision boundary, it's going to be a C of a subproblem. What's a subproblem? This is saying using coin say DL, some coin. I don't know which coin it is, but I'm assuming the first coin here is some specific DT. What is this then, the remaining subproblem? N minus DT. And in terms of number of coins, how do the two objectives relate to each other? What's the difference between the number of coins used in here and the number of coins used in here? It's 1, right? Because I use that coin DT. This is coin DT. Saying if you want to give change to N cents, you have to use one coin, the first coin, plus how many coins you use to give change to N minus DT. Right? So what do we need to look for in here? What is it, the boundary, effectively? This is DT, right? So we don't know that, and I think we need a search for it, right? So what I'm going to say is, let me move this on the other side, +1. That is from coin DT. I have to search. How do I search? I look for all T's. Right? I look for all T's. And I'm looking for what in here? Minimum. I could have taken this one out because one is a constant, I can put it outside the minimum argument, right? I just say minimum for this. So this is 2a. There's a 2b part, which is the subproblem table. Remember the table I mentioned last time? In this case, how many dimensions are on this table? I look at the arguments in C, it's unidimensional, right? Because C depends on only one argument. So here's the table, it's going to be a line, right? What is on this line? The sense. That's because it's the argument in C, the sense. So minimum is 0, maximum is some max, doesn't matter. Maximum is n. And where is C of n? C of n is right here, right? That's C of n. So this table does not contain the values. It just contains the subproblems. And I'm going to draw some arrows. What kind of subproblems I need to solve here? What subproblems I need solved in order to solve this one? I'm looking at my equation, and one of the problems I need to solve is n minus d1. Right? When I'm going to look for this minimum, I have to solve a bunch of subproblems here. One of them is n minus d1. Now I'm going to assume, let's assume that these are sorted. So what's another subproblem I need to solve? N minus d2. I'm going to put an arrow that says, to solve this problem, those are the dependent subproblems I need to solve. Another one, maybe this is a bigger coin. This is n minus d3. I need to solve this problem, right? And maybe the last one is n minus dk. So for the United States denomination systems, how many subproblems are going to be here? How many D's are for United States denomination system? N minus 1 cent, n minus 5 cents, 10 cents, 25 cents. So I need to solve k. This is from t equal 1 to, okay, this colon is MATLAB notation for all values between 1 and k. So part 2 includes two things: the recursive equation and the subproblem table. You can draw these arrows in any way you like. I prefer drawing this way, but you have to make it clear that if you want to solve this problem right here, you need the following 4 subproblems. Part number 3 of dynamic programming. Part 3. Bottom up computation. This is a pseudocode. In case you forgot, it's a computer science class. You used to write some pseudocode. So how do we compute, bottom up computation, we compute all subproblems in computation table. In this table right here. Subproblem table. Let me call it subproblem table. So remember this word all. We are not computing just some. It's true that the question is asking us for this, right? It's saying, give me the minimum number of coins to give cents, change back to n cents. We're not going to compute that one. We're going to compute all of them. And in what order? The order is given by those arrows. In order to solve this problem, we need problems before. So in what order should I compute all these problems here? The correct order is, this is the order of computation. Right? Because if I compute it left to right, by the time I get to any problem, I'm going to already have the subproblems computed. Right? So that's what I'm going to do. How do I write a pseudocode here to solve those problems? Shouldn't be hard. I can say C of 0 is 0. If I don't need, if n is 0, then I don't have to give no coin, right? And then I say for I equal 1 to n. Let's say, what variable should we use? Maybe L here. So I'm going through that computation table, right? This is some L. This L is going to depend off a bunch of subproblems that are already computed because I'm computing in that order, right? So how do I look at my recursion here. I'm going to say what? Say the minimum, I set it up to 0, or to infinity, sorry. And then I say for, I'm going through the coins, right? I'm now trying to compute this minimum. For I equal 1 to k, right? I evaluate so let's see, if 1 plus C of L minus di, that's the value in the minimum bracket. If this is smaller than the current minimum, right? It means I got a better coin to use now. So I have to say, make the minimum that 1 plus C of L minus di. This is simply computing that minimum. It iterates over all the coins and say which one gives me the minimum, right? I start with the minimum being plus infinity, and I figure out which is the minimum by trying all coins. Maybe if the coins are sorted, so okay, let's finish that. If this thing, then I finish the for loop, right? And then I have to set C of L equal with the minimum, right? Because the reason I compute the minimum is for C of L here, right? I've got the minimum, I store it in C. Now I finish this for loop. That's going to compute all C's from 0 to n. And I'm going to return C of So what did I do here? I did a bottom-up computation, not recursive. I know there is a trick to do it recursively. We pretend we don't know that. So it's going to specifically, unless I say recursion is allowed or something like that, I'm asking for the bottom-up computation. That is, the bottom-up means you have to start on the table somewhere that allows you to do all the computations in order. I couldn't start from here. Because if I start in here, I need some problems that are not solved. I couldn't start in the middle because, again, I need some problems on the left side. That's why these arrows are so important. It tells you where to start the computation. All the arrows point to the left here, which means if I solve it from left to right, at any point CL, I'm going to have the subproblems already done. So that's necessary in this line in here, right? Well, I'm at L. I'm going to use what I already have from L minus di. right? Which is already computed because the nature on which I build the array. That's what dynamic stands for. The fact that when I solve the problem for L, I already have solved the subproblems. And I can even do a search between the subproblem results. This is what's happening here, right? I'm searching through the subproblem results to see which one is the best to use. Now, it's true I don't have to try all the coins, right? Assuming the coins are sorted, do I have to really try all of them? Is there a point where I can say, don't try the rest of the coins? Somebody, hands up. So, if I can try all the coins, the issue is some of the big coins may not be necessary to try. Why?
Cost is lesser than the value of the coin.
The cost?
Is less than the...
Not the cost, yes.
You may have already solved that before. You may have already solved that particular C of something before.
Right, right. No, this is solved already. The question is, why not try all the coins here? There is a, when, at some point on the bottom of the table, I don't need to try all the coins. Yes?
Because you might have exceeded and
L.
Right.
If L becomes, say, 20 cents, what's the point of trying a 25 cents coin? Right? So I could say here, I still want to run the for loop, but I could add a condition. If the coin is bigger than L, I can not just not do the loop, but get out of the loop completely, right? Because once this coin is bigger than L, all the remaining coins, assuming they're sorted, are going to be bigger than L. No point trying them. So how do I say get out of the loop? Break the for loop or exit. Make sure when you write this in pseudocode, you want to write something like this, exit the for loop. Because you may say break because in your favorite programming language that's called break, and somebody who reads it may not understand what you mean because in different programming languages mean different things. If I would write something like this, I would make explicitly what I mean. I'm saying, assuming the coins are sorted, so I'm going to put here, assume coins are sorted with di plus 1 bigger than di. Once I see a coin that's bigger than the current L I need, there's no point trying it because that cannot be possibly used for L. It's too big. And that's going to be important on the bottom sides of the table. When L is small, if I have a lot of coins, suppose I don't have 4 coins, suppose I have 50 coins, right? Then what's the point of trying all these 50 coins if most of them are bigger than L? But that's optional. Okay, so that is part 3. And now we have part 4. Print solution. We're going to call it trace. But you can call it print if you want to. The problem is that this only returns the number of coins. So it says if you need n cents, C of n is 5. You need 5 coins. But we would like more. We just want the number 5. We want what? Which 5 coins are part of the change? So this doesn't do that, right? This solution gives you the number of coins, the minimum number of coins, but it doesn't say which coins you need. So we need to add something to keep track of those coins. That's not always necessary, but it's easier to add it to make it clear. So the way you have to think about this trace is, what do I need to keep trace from here, from this problem? I'm solving this problem. I have these arrows in this problem. how many of those arrows I'm gonna actually need? How many sub-problems I'm gonna actually need? I need to solve all 4 of them if they're 4 coins. But once I solve them, how many I'm gonna need? 1, right? Look at my recurrence. It says a minimum that says look to the sub-problems. But then once you know the minimums, you're only gonna use 1 sub-problem, right? It's not always true. Sometimes we look at the sub-problems and use 2 of them, maybe. So what I need to keep track is which arrow is the one being used, which sub-problem I'm using, right? So add to part 3 pseudocode. That's another reserved letter. S. You have to use S, and you cannot use S for anything else. For trace. So S of L would be which subproblem I'm using for L, right? So for any L, not just the last one, I need to know which coin is the coin that I figured out, right? So is the coin that you use coin dictates the subproblem. So where should I put that? Where I'm deciding what coin to use? Right here, right? This is what's saying you've got a better coin than before. Right? So I'm having 2 updates here. I'm not just updating that minimum. I'm adding S of L, because I'm at L, right? Is I, or DI. I is just the index. I need to keep track. So this is tracing the coin used at n equal L. Now what's happened if later on I find a better coin? I'm going to change the minimum, and I'm going to update what coin to use at L. So this is keeping track of the minimum also, or what is that first coin that's being used, right? So how do I write this pseudocode of tracing now? Of course, I'm going to have to return C and S. What is the first coin? The first coin that so I have n cents, here they are. How do I know which is the first coin? S of n. That is the trace for L equal n, right? I trace which coin was the one being used. What is the next coin? It's S, but of what?
N minus S.
N minus ds of n, right? Because S of n is an index. D of that index is the coin. This is the denomination remaining, right? These are the coins being used. So how do I write the pseudocode? Start with L equal n, while you guys are going to figure out the condition here. What coin do I need? Print coin. What's the coin I need? S of L. Right? S, remember, keeps track of the first coin I need for that value. And then change the L, right? What is L now? L minus? You guys are stunned.
Yes.
We haven't seen dynamic programming when we were undergrads? No? I think it's part of the undergraduate curriculum. Yeah, this is a fancy version of it. So what is, once I give that coin, what is the remaining L, this part? L minus D S of L. right? And you guys have to figure out how much do I go. I guess L, as long as L is. So this is gonna print the coins I'm using, right? Remember that C is reserved for the objective recurrence, and S is reserved for tracing the solution. Now, it is true that in some problems, tracing can happen without additional S. In here it cannot. In here, just from the C's, if I tell you, okay, for 300 cents you need 7 coins, you can't immediately figure out, even if I tell you the number, you can't figure out immediately which coins are the 7 coins that you need. That's why S is necessary here. Keep track of the S. It doesn't consume additional running time, right? This is, for every one operation that I do here, I do 2 instead. So it doesn't add to runtime. It adds to the memory, because this is S of L. Now I have, instead of 1 array C, I have 2 arrays, C and S. So it does add to the memory space. But then this L keeps track of the first coin to use for L, for every L. And then I look at my cents. I give the first coin, which is S of L. So I traced it. And then I say, what was the remaining subproblem? L minus that coin. And then again, I look at my S for that subproblem. What is the best coin to use first? Part 5, which I'm not going to do here, is an analysis of the running time, which is for every algorithm we do. So if we are to analyze the running time of this algorithm, what do we get? I mean, this is easy, right? We can analyze it without thinking it's dynamic programming. Doesn't matter dynamic programming or not. This is a for loop of k things. Inside the loop is constant. So this is theta of k, and this is. So what's the runtime? K is fixed, is the number of coins. That was our first dynamic programming exercise. So I think the problem you had, I'm not sure you had it, was using denominations at the powers of 2. Power of C. Okay, and in that case, it asks you, of course this is true, this solution works for any denominations. But this solution implies this search here. There is a for loop inside, that's a search. So it makes it n times k. For every n, I need to do a search of k items through all the coins. I think the problem you had was asking you, can you do it without dynamic programming? Can you have a greedy solution? That's true only if denominations have a certain aspect. Okay? Like I think if they're powers of 2, 1, 2, 4, 8, 16, you can prove mathematically that the best thing to do is to use the bigger coin all the time. You don't have to worry about sub-problems. I give you guys an example, or that was office hours, I think. Can anybody remember that example? What was it of denominations for which greedy wouldn't work? 1, 6, 13. If I choose n equal 18, suppose I do greedy. Greedy means use this coin first, 13. But then the remaining change is 5. 5 forces me to give 5 ones. So the total number of coins would be 6. But I could have done much better than 6 by using 3 sixes. So this is an example why greedy fails. Now, I'm talking about the obvious greedy strategy. You could say, maybe I come up with a different greedy strategy, right? Like in the activity selection, it's not obvious that the biggest coin is always best. You can play with that. But in general, you can see how at least the obvious one fails. So you had in your I don't know if it's in a homework. What if I have 1, 2, 4, 8, 16, 32, and 64 denominations? Now for any n, Greedy says what? Choose max coin smaller than n, right? I think that works in here. In this set of denominations, choosing the max one is guaranteed to give you the optimal solution. But you can play it out. And I don't think that's the only requirement. I mean, you can find some other denominations for which greedy might still be a valid solution. I remember one problem that asked for denominations being Fibonacci numbers. 1, 1, 2, 3, 5, 8, so on and so forth. Is it greedy in that case? Can you just give the biggest number that fits in? Okay. If it is, you need to prove that works. So let's add here for the meter problems. Coin change with particular denominations, like powers of 2 or Fibonacci, and maybe other sets. So in this case, this coin change might be a greedy problem. But in general, it's not. If you want to solve the general coin change problem, that is the dynamic problem. Okay, so let's do one more. Next problem, we call it the checkerboard. So the checkerboard problem. Here's this problem. We have a checkerboard with, say, what is it, N and M? I think. So this is from 1 to N, and this is from 1 to N. So checkerboard is N by N values. We're gonna call this P of ij. So let's say this is an I here. This is a J. That's P of ij, or Pij. Is the penalty for stepping in cell ij. The task is start anywhere, start somewhere on row 1, move n, I guess n minus 1 steps. The allowed move is when I'm moving from any row, so this is the current row, and I'm here. The allowed moves are, you can go up, up right, or up left. So if I'm in here, the first row I start in here, I could go here, or here, or here. But now suppose I go here, then I could go here, here, and here. And now I go here, and I could go here, here, here. So every time I go somewhere, I could choose. So I choose this path, and then this path, and then this path, And then again from here I have three options. Suppose I choose this one. So I'm here. Now again I have three options. Suppose I choose this one, straight. Again, three options. Suppose I choose this one. And now I'm in the final. I need to reach and reach row n. First I need to do n minus 1 moves because every move advances me one row. The decision is where to start. I can make that decision. And at each step, which one of the three options I take. And the objective is minimize the sum of penalties. That is the penalty for the path. So the penalty is associated with every cell I step in. The cells should be this, and that. Whatever penalties are in those cells, I sum them up. I want to minimize that. Let's assume that these penalties are positive. So though, I think it works to negatives too, but I don't want to worry about that right now. That's a problem, right? I want to get from here to here and find the minimum path through this thing. I'm also going to assume that this is circular. Doesn't have to be, but it's easier if it's circular. That means if I'm in this cell at the extreme, I still have three options. Those two are obvious, but where is this one going? Coming on this other side. And from here, if I choose to go right, this arrow is coming in here, right? So I'm assuming this is a circular matrix. It's not necessary, I can solve it without being circular, but for simplicity, any move that steps into the n plus 1 cell column, so the circular means the n plus 1 column is actually first column. And the minus 1 column is 0. You can do this very easily with modulo arithmetic. Modulo arithmetic will take, I mean, it's starting at 0 for modulo arithmetic. Instead of 1 to n, you get 0 to n minus 1. And every time you say n, you're back to 0. And every time you say minus 1, you're back to n minus 1. That's how modulo arithmetics work. This is not necessary. I could restrict the options for the last cell to be just up and left, if I want. It doesn't change the nature of the problem, but just to stick in here with the dynamic programming part and now with those details, let's assume I can, whatever I say 0, it's actually going from the beginning. Whatever I say n plus 1, it's moving to the first one. Okay? So part 1. We need to characterize the optimal solution. So, like always, we start with, okay, what if somebody gives me a solution? What is a solution? What is going to be written here in this solution? The steps, right? So it has to be what? What's in here? This value V1 is what? This is the column, right? Column on row 1. So this is saying which column in row 1 you start on. This V2 has to be column in row 2. And this Vn is the column in row n. So because if somebody gives me this, this is clearly a path, right? Assuming that Vi plus 1, so that to be valid, every Vi plus 1 has to be which one of the possible, 3 possibilities, right? Each Vi plus 1 has to be either Vi, same column like the previous one, if I move up, or Vi minus 1, or vi plus 1. Again, in here we're assuming circular. So plus 1 if it's at the end becomes verb in the beginning. And, right? So for a solution to be valid, this must happen. Every v, this is, vi can be anywhere. Not vi, v1. Anywhere. So this is for every I bigger than 1, right? The first one could be anywhere, but after that, the next one has to be either on top of it, or one left, or one right. Okay? So where should I break this solution? I'm going to break it at one cell, which is a particular cell in the table here. Say, break it here. This is the decision, or the break one. And in this cell, I have 1, 2, 3, up to n. Those are the rows. So this cell corresponds to a pair. So the decision is the row k and column vk. Right? That's right here. This is the row k and the column vk. Vk is part of the solution. So what am I saying is, if this path was optimal, this subpath must be the best way to get from anywhere on this row to exactly this cell. Not to this row, but to this particular cell. And the rest of the path has to be the best way to get from exactly this cell to anywhere on the top row. Is that true or not? Yes. Exchange argument. If somebody can find a better path to go here, I can take that better path, put it together with the rest, and that's a better solution, right? So what are the sub-problems here? The two sub-problems. One is from the row 1 anywhere to this cell, the cell, let's call this cell KVK, right? And the other sub-problem, let's say anywhere in row 1. The other sub-problem is from anywhere, from KVK, from that cell to anywhere in row n. So these are problems. If this is an optimal solution, I take that solution for these sub-problems, it's gotta be optimal. Again, if it's not, there's a better path, then I can construct a better solution. Okay? How about the part 1b? If I have optimal solution for those sub-problems, how do I glue it back into a whole path? What assurance that I can glue it? There is something in here that says you have the path from here and a path from here. Those two paths can be put together. What in here gives me that property that I can put them together? This cell, right, is the same cell. If I just say, here's two sub-problems, get from here to here, and then from here to here, even though you find the optimal paths, that doesn't give an optimal path from the bottom to the top. The gluing is in this cell that's in common. So the KVK cell, common, means the sub-problem solutions can be combined into optimal solution. The only problem, of course, like in coins, is that I don't know where to break it, right? If I can tell you this is the cell that you need to break, you would call recursively, find me the best path from here to this cell, and then find me the best path from this cell to the end. The only trouble is, we don't know where to break it. So can we decide where to break it in advance? Before solving the sub-problem, can you say, I know it's gonna pass through this cell. If I know it's gonna pass through this cell, I can break it at the cell and solve the two subproblems separately, but I don't know if it's gonna pass through this particular cell. So the part 1C is we need to search for the breaking cell. So part 2. I think you guys, if you follow what I did before for coins, we should be able to follow here. So I need this C, the objective. The C is gonna be, it's an objective, so it's gonna be the minimum path penalty, right? This is part 2. C is gonna be of what? When I move from subproblem to subproblem, what's changing? In the coins, what was changing? N, the number of cents. In here, what's going to change? I think it has to do with this cell, right? If I decided I'm going to break by a cell, my decision cell, I think this cell is going to be the argument for my C. So let's say IJ. That's a cell. So this is going to be in English, minimum path penalty of a path from row 1 anywhere, so anywhere in row 1 to cell IJ. That is my C. Is this. The best way to go from row 1 all the way to the cell. So how do I do this recursively? This gotta be, well, how can I get here? I have to come from the bottom, right? The only way to come here is from the bottom. But I don't know which one of the bottoms I'm coming from. So how many options are there? Three options. There's going to be a minimum of which? So I can come from, I have to come from the previous row, so that's certainly I minus 1, right? And that could be from j minus 1. That is, let's draw a nice thing here. This is ij. And out of the 3 possible cells, which one is this one?
Left one.
This coming from here, right? Okay. Or I could come from I minus 1 and j. Or I can, this is corresponding to what? Coming from going up, right? And the other option is to come from where? I minus 1 and j plus 1. That's corresponding to coming from the right. These are the options for that C. A minimum, of course, of 3 things. I don't have to put an argument to the minimum. It's minimum of that and that and that. Now that's not true. That is for I guess this is when I is at least 2, right? Because it does not apply to the first row. On the first row, I don't have this condition to come from one of the 3 in the bottom. This applies here, 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 everywhere, but not on the first row. Hands up who's with me. Okay. So on the first row, I say if I equal 1, what is the penalty to step on a cell? Right? Cij is going to be the penalty. I only have the first row here. If I choose a cell, I can choose any cell I want. What penalty do I get? It's not a minimum. if I step on that cell, I automatically get the penalty. Yeah. Now this minimum is the best way to come all the way to here. That's coming in the minimum. It's either this or that, but I need to add the penalty for stepping in. This path is all the way to the cell ij, so it says you come somewhere, either to here or here or here. That's the minimum of the tree. Plus, you need to step on. So how do I do that? It's Pij plus this minimum, right? Because Pij is guaranteed. If I decided I go to cell ij, then for sure I'm gonna step on Pij, and then I could come to any one of those three things. I check the minimum. So what is the computation table gonna be looking like? I'm going to look at I and J. Those are the parameters in my thing. I and J. And I'm saying for any particular problem, this is the problem I need to solve necessarily? No. I need to get anywhere on the last row, right? No, sorry. The way I draw it, let's put I here. I is the row, J is the column. I need to get anywhere on the last row. So I'm not sure which one of these I'm going to need, to be honest with you, right? Because solving, the problem doesn't say end up on this cell right here. It says end up anywhere. But to solve any one of these problems, which are the subproblems that I need? Look at my recurrence. The three below, right? So this one will depend on this problem, and this problem. Right? This one here will depend on what? This problem, and this problem. This one here will depend on what? This problem, and this problem. So remember in part 3, I have to compute the whole table. Bottom-up computation of all problems. In what order should I compute this table such that when I get to any problem, I have the subproblems already computed? Fill it from the first row all the way up, right? Does it matter in the row which way I do the computation? No. Because it depends on the previous row only. It doesn't matter if I start this. If I have multiple problem on this row, I could do it right to left, left to right, because it only depends on the problems below, which are already computed. So the critical part here is to make sure when we compute this table, we do it in the order that allows any problem to have the subproblems done. So how do we do that? Part 3. Pseudocode, right? First, C of the first row and everything. I'm going to say all here. So first row, all columns, is who? On the first row? It's just P. So it's P of all the first row and all columns. Now, if I'm to write that computer sciencely correct, I have to put a for loop, right? For j equal 1 to n, C of 1j is P of 1j. But we allow this in pseudocode. Then I start this computation, right? I do it bottom up, starting from the first row. So for I equal 2 to n, for j equal, I need to do all columns, 1 to n. I'm going to write Cij exactly like that recurrence, minimum of the tree, Ci minus 1, j minus 1. C of I minus 1 J, C of I plus 1, I minus 1, J plus 1, right? That's ending this loop now, right? Then I'm ending this loop. And then, what do I have to return? I've got the C computed, which means I have all the values filled up. Now, there's no constraint on when to end up on the last row. So, what do I do on the last row? So like in coins, I return C of n because there were n cents. In here, I can't return C of this necessarily. Minimum on the top, right? Out of all these possibilities to end up, every one will be computed now, every C. I have to say, now find T, the minimum over all C of the last row is n, and all, that's its arg minimum. Let's say T here, right? So it says, this it reads like find the minimum on the last row out of all columns. Arg minimum is the argument that gives that, right? And I have to return what? C of n comma t. So out of all the penalties incurred to the last row, I return the minimum one. Because there was no specification, you gotta end up in a particular cell. Any cell is good. I'm gonna check to see which one allows me for the minimum. Now, is this problem greedy? What makes it non-greedy? Can you, at this point, decide which one of the three options? Suppose I tell you where to start. Can you immediately decide which one of the three options is good to take? No, because even if there is one small and two big, this one small may get you stuck into some very bad options later on, so you need to choose a big one maybe that has a smaller path after. And there's no way to tell that until you actually check the path. That makes it dynamic. So everybody understood this? Out of all the last row, I check which one's the minimum and I return that. Now part 4, of course, is I need to print the solution. It's not just returning which is the minimum. So far I know I want to get to this cell, that's NT. And I also know the penalty, the overall penalty. That is the value. C of NT is the actual penalty incurred on the path. That's the minimum penalty. But it doesn't give you the path. The path, like in optimal solution, is a bunch of columns. Tells you for each row what columns to step on. So we need to keep track of that. How do we keep track of it? At each, again, we need to keep track for every problem. Which one of the, it's only one out of the three, right? I'm solving 3 subproblems and I'm choosing one of them. I need to keep track which one is being used. So every time I compute Cij, I'm also going to compute Sij. That's going to be arg minimum in terms of the T, the column, between the same thing, just like before, right? With T belonging to either J minus 1 or J plus 1. So Sij will only record what? If this is Ij here, Ij, who's Sij? It's either J minus 1 or J plus 1, right? This is J minus 1, J plus 1, of course on row, I minus 1. So Sij will tell you which one of those 3 has been used to get to J. So it's admin over this thing in this column. Of course, this row is fixed here, so I don't need to keep track of the row. It's always the previous row. I need to see which column is it. Let me write this nicer. So this is R mean for T belonging to J minus 1, J plus 1 of the whole thing. C of I minus 1 T, C of I minus 1, C of I minus 1 J, I can just write this. Of course, in practice, when we implement this, you don't compute the minimum twice, even if it's only three things. You check which one's the minimum, and you immediately update both the value and the index that has been used. Okay, so how do I trace the solution? Assuming I have that, how do I actually print out those columns? I start from where? What's the first column that I'm going to print? S of N and T, right? And then the next column is going to be, I have to update who? N I know how to update, right? It's certainly going to be the previous row, guaranteed. The question is which one of the columns I'm in, right? So if I'm here, how do I know the previous row was this one? So I need to update T into, the T is the last T initially. Now, who's the previous T, the previous column? S of
N minus 1.
Okay, so we're confused. Right?
What is it?
So who's S7 of T? Who's this? The C is the penalty. But who's S in here? Is tell me which column is on the previous row. Right? So let's write this nicer. The first one is S. So the first cell is NT, right? The next cell is T becomes now S of NT, and the output is going to be N minus 1, and let's call this T0, and this is Tn. This is Tn, this is Tn minus 1. Now, of course, Tn minus 2 is going to be who? S of N minus 1 and Tn minus 1. So now what I'm going to output? N minus 2 and Tn minus 2. So if I want to write the program, I start with NT. NT I return from here. So I start with NT. And then I say print while condition, print NT, and then what's the update? N becomes N minus 1 always, and T becomes S of NT. Make N decrease N after I update T, so I don't run into problems. And I keep printing until N is at least 1. So can I do this without trace? If I don't have this S, can I still print the solution in this particular problem? So suppose I don't have an S. I have the C and I have the T, which is which column I need to end, the best way to end up with. How can we trace the solution without while N at least 1? I'm going to print N and T, right? I'm going to need to update T, and then I need to update N. That's easy. How can I update this T without having S? Minimum of the three under it, right?
Yes.
So this is going to be the minimum between who? C of N minus 1
J minus
So it's arc minimum. Arc minimum in T minus 1 or C of N minus 1 T and C of The reason this is acceptable in this problem is because the number of things to check in here is fixed 3, so it doesn't add significant computation. It's still O of 1. Right? In the other problem, the number of coins was a variable. If I look for a minimum at the tracing solution, I'll have to add computation because I have to do k steps. It's better to keep track. In here it's for free. Since I check all the possibilities, keeping track of S, it's not additional computation. In here, it might be or maybe not. In this problem, it's not because minimum of 3 things, it's a O of 1 operation. But in the previous problem, doing this at the tracing will add computation to the solution. If I were you, until you develop a better dynamic programming sense, I would always keep track of this S. So I don't have to worry later on, oh, I could have done it with this. Unless the problem specifies, don't keep track of the solution, just do it from the computation table C. Try that, but in general, I think it's just easier because in here, it never adds computation. You already know you're searching for the decision boundary, right? So you know which one you use. You can just store the one you use, and that is what you need. So tracing the solution means keep track of the subproblem you need for every problem. That's what it is. And since we're already searching for it, we just have to remember that. Before I stop, I want to talk a little bit, give you a hint or something. Next time, that is Friday, we're going to talk about discrete knapsack. So discrete knapsack. You don't have to write this because it's just something to think about. I have a bunch of items like before they have values, VI and weights. And there's a knapsack capacity, Z. The problem is the same as before. I need to maximize the knapsack by not overloading it. And I need the maximum value, right? Same like before. First of all, I hope it's clear in here that no greedy strategy would work. There's plenty of examples where picking the smallest weight or the biggest values or even biggest weight by value. I think there was just one second. Here's this example. Value is $60. Weight is 10. Value is $100. Weight is 20. So this is the weights. This is the values. Value is $120, and this is 30. This is $150. This is 50. So what's the biggest value? Say Z is 50. What's the biggest value here? 150, right? That will fill my knapsack. What's the smallest weight? 10. So one greedy strategy is pick the biggest value. Another greedy strategy is pick the smallest weight. And the biggest value by weight is what? 60 by 10 is this one. Neither this or this are correct. The best way to fill this knapsack is to put those two inside, which are neither the biggest value, nor the smallest weight, nor the best ratio of value by weight. Just to be clear, no greedy strategy works here. My question for you to think for the next time, which we're going to do all parts, is directly jumping to the computation table. What do you think the computation table needs to be for knapsack? One axis is going to be Z, for sure. But what about this? That's what I want you guys to give some thought. Because in the midterm, last year I had a complicated knapsack problem where the fundamental trick was to figure out these axes here. So in here you need the items, obviously, right? because items are a parameter. Once you start putting things in, it's not like the coin, you know, like you have a bunch of those. You put this one in, it's gone. So we need an item set, right? The problem with knapsack that the other problems don't have is that if you write all the possible subsets, right? Because the other axis when we draw this table were all possible columns, right? Or something like that. This is going to be exponential in the number of items, right? So if I say the number of items is n items, and this is 2 to the n possibilities, and then I say compute all the computation table, right there I'm going to have 2 to the n computations. That's probably not good, right? No exponential we can do. So in knapsack, it's not a hard problem, but we have to decide what do we do about this axis, the items axis. We can't just put all possibilities in there. All possibilities are too many. That's on Friday. Okay? Yes?
I think we need to add PRJ here.
I think so too. In here?
Yeah.
How about here? Why not? Because it's the same, it's adding up to everybody the same. You won't change which is the mean. Yeah. Very good. Can we stop the camera? This is a red button on your side. That side.